Welcome everybody to today's webinar of the IEA SHC Solar Academy hosted by ICES. We are very pleased to have all of you here, and we are especially happy to welcome our speakers and you, the audience, to the webinar. We are now good to go. My name is Arabella. I am the Congress's Communications and Outreach Officer here at the ICES HQ in Freiburg, Germany, and I will give you a short introduction into ICES and the work we do, as we have many new participants joining us on the webinar today. So, ICES, who are we? ICES, the International Solar Energy Society, is a non-profit UN-accredited membership NGO, and we were founded in 1954. ICES represents a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses, and advocates from countries all around the world. Our vision is 100% renewable energy for all, used efficiently and wisely. And ICES works together with like-minded organizations from countries all around the world, such as the IEA SHC, to advance our renewable energy transformation. Here at ICES, we have a range of key activities to advance our mission. We hold biannual congresses all around the world. One is the Solar World Congress, and one is the conference series called Eurosun, which is now in cooperation with IEA SHC. We have two major publications. One is Solar Energy Journal, which many of you will be familiar with. It's a flagship publication which started in 1957. And then just now in 2021, we were very happy to add to that our Solar Energy Advances Journal, which is our first fully open access journal. Of course, there's much more to it, and we also do webinars such as the one today. We have education initiatives both on-site during our conferences and also online. And we have a set of infographics, and on top of everything, we also have, and we are very proud of that, a solar energy museum in which we trace back the history of solar and the many important developments over the past decades. We are a membership-based organization, and so we invite all of you to join ICES to advance our renewable energy transformation. So for the webinar today, I know we are all excited to get started. Yes, there will be a Q&A session for you, the audience, and we're going to have that at the end after we have heard all presentations. Nevertheless, you can send in your questions all throughout the webinar, and you use the chat box on your GoToWebinar panel for it. If you send in a question, please keep the question short and precise and write who of the presenters your question is for. That's going to make it a lot easier for our moderator to then send the question to the right presenter. And on that topic, I'm very happy to introduce our moderator of today, Babel. Babel has been with us for many of the IEA SHC webinars, and we are always very happy to have her back. She is the founder and managing director of the German consultancy SolarPACES. She also is responsible for the international newsletter on the portal Solar Thermal World, where she reports exclusively on market and technology trends in the solar heating and cooling sector. And also, for many years, Babel now has been the chapter author for the annual Global Status Report published by REN 21. So it's my pleasure to hand over the floor to you, Babel. Welcome.
Yes, Arabella, thank you very much. Good afternoon also from my side. Yes, I will share with you some slides on what is the IEA Solar Heating and Cooling Programme. Will this work? Oh, sorry. Can you share it again, or was it already shared?
We see your screen. And
oh, you see my screen already?
Presentation is there. You just,
presentation is there.
I think you have to go back.
My presentation is there. Sorry for that.
Yeah, there we are.
Okay, sorry for that. Okay. Yes, we have, together with ICES, a very nice and long-going webinar series. It's called Solar Academy IEA SHC. Today we have the interesting topic of solar process heat, and I will give you some insights on the IEA Solar Heating and Cooling Programme. It's a research-focused collaboration. 19 member countries and 8 international organizations cover a big range of countries. You see them colored here on the map. You have the red ones, which are direct members, and the orange ones, which are members via sponsors. more than 200 experts from industry and research work together on dedicated solar projects. So we have a lot of topics which are listed here, you know, like water management, we have solar cooling in the Sunbelt region, we have neighborhoods, we have solar hot water for 2023. So we cover a wide range of applications in solar heat. The Solar Academy is the webinars we host with ICES quarterly are one of the activities of the Solar Academy, but there are also others. We have a video channel on YouTube where we have recorded a lot of YouTube's videos with experts on conferences. And what is very important, we offer on-site and online training with solar heating and cooling topics on request of IEA member states. And the last of the such trainings were in the Caribbean, in China, South Africa, and the UK. You want to find more information of our organization, you can go to the website iea-shc.org or follow us on the social media that you find here. Also the YouTube channel I mentioned already. If you want to search for the Secretariat, we give you here the contact information. And then I want to stress your attention to our flagship annual solar heat report, which is published once a year in June. It's the most comprehensive data gathering on solar heating and cooling technology and market trends. And you'll find it also on the website available as a PDF, and you can consult it and also quote it in your own presentations. So this was my little introduction. I'm happy to welcome you today to this Solar Academy webinar on solar process heat. The IEA SHC is organized in tasks. So this is how we call the research programs. Solar process heat has number 64 already. And we have 3 dedicated experts from this task who will present some of their work today for us. This task is a 4 years research program, and they are almost at the end now. They have 1 year to go, so we already see a lot of results coming up. So the first speaker today is Felix Pack. He is researcher at the Institute of Thermal Engineering at the University of Kassel in Germany since 2015, and he became head of this group in 2019. He's currently working on his PhD, looking at a combination of solar collectors with CSP in industrial applications. Within this task 64, he chairs the subgroup on integrated energy systems. And he will present today about the role of SHIP in industrial hybrid energy solutions. So Felix, I'm looking forward to your presentation.
Yeah, thank you very much, Babel, for the introduction, and welcome to everybody here in this webinar. I hope you can now see my screen, and as Babel already said, I want to talk about the role of solar heat in future industrial hybrid energy systems. Within task 64 subtask A, we focused we focus a lot on industrial heat load profiles, and there we found one thing which is which not that much attention has been paid to so far. So very often, if people think of industrial heat load profiles, they have a constant and flat heat load profile throughout the year in mind. And what we found, based on a broad database analysis, that very often we see also in industrial companies heat load profiles which are very seasonal. So we have a strong dependency of the heat load profiles throughout dependency of the heat load on the ambient temperature. So here's one example from a car manufacturer, and we can see very clearly how the heat demand is increasing with decreasing ambient temperatures, at least on a daily basis. What people have more often in mind is a load profile or a correlation of the heat demand and the ambient temperature, as we see it here on the right side, which is an example from the food and beverage industries. And here we can see the non-dependency of the heat load profile of the ambient temperature. So that is really one thing which is very important to keep in mind. How does the heat load profile looks like, and what is the influence on the overall system design? In subtask A, we yeah, we did some more work on that, and we did a cluster analysis of more than 500 heat load profiles. Unfortunately, these profiles are mainly from Germany. We think that yeah, the basic results can be transferred also to other regions throughout the world, at least in these regions where we also have kind of a yeah, seasonal behavior of the ambient temperature. And here in this diagram, you can now see the results of these cluster analysis. So we have in blue these profiles who are very non-seasonal and flat throughout the year. And for different industries, you can see how the heat demand is really increasing with the ambient temperature. More information on that, and because we think that is very important for the future system design, you can find in this deliverable, which is shown here, the reference applications for renewable heat, which is published on the task website. And there you can also find an Excel tool where you can make your own heat load profiles. So I have already shown in the on the last slide these strong dependency of these heat demand clusters and the ambient temperature. And here in this picture, you can see the combination of the clusters and different sectors, and how the different clusters are distributed within these sectors. So to give an example, again here, the manufacture of beverages. At the bottom here, we have in all our profiles that we had, that all these companies were were collected in this cluster 0. So in these clusters where we don't see any seasonal behavior, and that is very different in some other sectors. For example, in the manufacture of computer, electronic, and optical products, where we see more processes who are related to the ambient temperature, for example. Or basically, this is very often space heating, but also very important are big ventilation units, who are often underestimated in their importance for the industrial heat demand. One other thing that we took a look at in the subtask was the importance or the availability of roof area for solar collectors. Very often in potential studies, we found that the availability of roof areas are a limiting factor, but so far we could not quantify it. Based on the database that we had, we could make an analysis with GIS data from OpenStreetMap and analyze how often the roof area is really a limiting factor, and what is the influence on this potential solar fraction that we could reach with these solar collectors. And the results you can see here in this diagram. So on the y-axis, you can see the required collector area based on the summer heat demand. So the solar system design is always made in a way to really meet the summer heat demand and not to produce too much excess heat in summer. And on the x-axis, you can see the flat roof area that we find based on the GIS data. And always, if you see now, so one dot is always representing one of the companies in our database. And in all cases where the company specific dot here is below these lines, then you know that the roof area is big enough to install that much solar collector area to really meet the summer heat demand. And the good news is that only 40% of the companies that we had in our database had a too small roof area to install enough solar collectors. So basically, this is a quite good result, as 60% had enough roof area. Nonetheless, it also underlines the importance of having already during the installation of new industrial areas, also having already there in mind that you need to have enough perhaps additional areas to install solar collectors. So what is now the influence on the solar fraction, both of the roof area and the load profile. Sorry, and here you can see yeah, again, a combination of these both analyses. On the x-axis, you can see now here the relation of the collector area that we calculated based on the load profile, which is possible, divided by the available roof area. And on the y-axis, you can see the solar fraction. In this case here, again, every dot is representing one company. And here the roof area is not yet seen as a limiting factor. So this is really just what is possible based on the roof area. And we can see here, blue are these load profiles with which are quite flat. So we can see a high summer heat demand where we can, and based on this, we can really reach a high solar fraction in the range of 30 to 40%. But the more seasonal the heat load profile is, the smaller is the solar fraction if we design the solar collector field according to the summer heat demand. If we now also take into account the available roof area, then the picture looks already a little bit different. Then we see always if the roof area is a limiting factor, the solar collector area has to be decreased based on the available roof area, and then also the solar fraction is partly massively decreased. And this is especially the case in these companies where we have a high summer heat demand, so especially all these blue dots here. And based on the median, you can already see the decrease of the potential solar fraction that we can reach. So what is now the yeah, what's now about the combination of solar with other technologies, which is what really one basic part of the work that we do in subtask A. Based on the analysis of the load profiles and the available roof areas, I think it's quite clear that there are a lot of applications where we have to combine solar with other technologies, and we put an effort on the combination of solar and heat pumps in subtask A. And we were quite surprised in the beginning of the subtask work that everybody is talking about the combination of solar and heat pumps, but if we talk about details and really how to design the systems, everybody has its own strategy, which is based on its own experience, but there's not yet a really established common system design methodology. So what we did is to analyze a lot of parameters with a simplified calculation model, really to find out what are the most sensitive parameters. So as you can see on the right side, one basic idea was to have a look at different system designs. On the one hand, having solar collector field and heat pump completely in parallel, and then also two system designs where the solar collector field does a preheating and the heat pump ensures the set temperature, and vice versa, that the heat pump is doing the preheating and the solar collector field is designed to really reach the set temperature. And we wanted to find out which are really the basic parameters that are influencing our system design or our economics. And I cannot go into all details, but I want to show you one slide which is kind of summarizing what we did and which is going to be published soon, hopefully in a solar energy and advances paper. That here you can see in all these diagrams the levelized cost over 20 years for the different system combination of solar and heat pumps, and some parameters that are less important here at the top. So the location, the hydraulic concept, and also the annual load profile type are not that important for the economics of the system. Of course, you have different system designs and different solar fractions that you can reach, or renewable fractions, but for the overall economics, it really does not make too much of a difference. But here are three other parameters that are really making an impact and having an impact on the levelized costs. And on the one hand, this is a daily load profile. So is the heat demand throughout the year more or less constant, or do we see a peak during noon, or at least during the day? So that's really because that has an impact on the system design of the heat pump, and that you can see also here, shown by the heat pump capacity ratio, which is defined as the heat pump capacity divided by the maximum heat load, which we can see throughout the year. And here we could see that a strong under-dimensioning of the heat pump has really a system on the levelized cost, but the lower the heat pump is designed, the lower is also the amount of heat that can be delivered by the heat pump. So that is kind of a trade-off that you have to do. But going into the direction of 100% renewable systems, our proposal is going to the direction of a 0.5, 0.6 heat pump capacity ratio system design. And also quite clear, the source temperature for the heat pump has a relevant impact on the efficiency, and so also on the levelized cost of heat of the overall system. Again, if you're interested in more results on that, I invite you very much to have a look at this paper if it gets published soon. So to summarize, heat load profiles in industry cannot be assumed to be constant, as this is done very much. It really depends on the location that you look at, and on the sector of the industry where you want to integrate solar collectors. But the good message is almost all companies have a relevant summer heat demand. So there's always a role, at least in minimum, to cover the summer heat demand. Another conclusion, the roof area is a limiting factor for solar system design, but the majority of the companies really has enough roof area, and that is always the easiest option, not always the cheapest option, depending on the availability of other areas. But nonetheless, it's quite important to see that roof area is not a limiting factor for all companies. And one really important result based on our subtask A result is that we need new design strategies for solar heating plants, especially in combination with other technology, especially in combination with heat pumps, but also having in mind that the heat load profiles are very often not that constant. And so if we have the heat demand in winter or the transition times, but the solar yield in summer, we still have to see how to really better combine that to reach higher solar fractions or renewable fractions. That's what I wanted to present. I thank you very much for the attention, and I'm looking forward to your questions in the Q&A session afterwards. Thanks.
Yes, Felix, thank you very much. Very interesting. I think especially this hybrid combination, because we need to go to higher shares. So there will be always this offering of hybrid solutions in the future towards industry. Very interesting. So we will have all questions, as Felix said, at the end. And I want to stress as well the fact, if you take part in the webinar on Thursday morning and you're listening to the recording, we also encourage you to type in your questions, because we can read them out at the end of the recording, and we will answer them also in the following Q&A session. So both ways are possible. So then we have our next speaker. I want to welcome Dr. Alan Pino. He is researcher at the Energy Engineering Department of the University of Sevilla in Spain, where he obtained his PhD about solar integration in microbreweries. He's particularly knowledgeable in the field of solar resource assessment and integration of solar energy in industries. And Alan is originally from Chile, where he worked at the local Fraunhofer Institute in Santiago before. So today he will share with us insights about evaluating the uncertainty derived from ship plant simulations. A challenging topic. I'm looking forward to your presentation, Alan.
Yes, hello to everyone. Thank you very much, Babel, for the introduction, and ICES and HHC for the invitation to this webinar. So as Babel said, I will speak about the evaluation of the uncertainty related to the simulation of chip plants. These activities are part of subtask C of task 64, and the leader of the subtask is José Miguel Cardemil. And all the other authors that we have listed here, we have self-defined as a core team because we have not done all the work that I would present, but we were organizing and exchanging information with all the other participants of the subtask. So first, to start with the objectives of the subtask, it is to develop, well, collect in the first place and develop new information about simulations and monitoring tools for assessing the energy yield, especially for chip plants. And the most remarkable item here is that we want to address the known uncertainties that affect or impact the simulation results. For this, as I said, we first collected information because we're not starting from scratch. Task 49 was done several years ago, so we identify and evaluated the available simulation tools that we started from there, and all the new tools that have been developed in these years. That was, well, the first part of the task. So this is a 4-year task. The 2 years, well, almost 3 years are already completed, and these 2 main objectives we have achieved, and the next one for the next year would be the 3rd one. So the second objective, so this is the one that require more effort and more activities, is to assess the uncertainty that we can have in modeling simulation, modeling chip plants in different simulation tools, especially those that are developed for solar process heat systems. I will speak mostly on this. And then the last part of the task, which we are launching in the next days, it's to do the yield assessment for the monitoring stage during the operation of the plants. So this way it would be easier for the client and also the supplier of heat to have clear measurements or some guides in order to understand and to improve the contract, because it's very customized right now. This subtask is also related with the other subtask, like the one Felix just presented, and the next one that Wolfgang will. What are not objectives of this task is to make a ranking of the best tools for simulations. That is not possible because it depends a lot of the user, and also, well, it won't be fair to many tools, and also we are not wanting to create a tool that is the reference or the standard to simulate chip plants in this case. So just wanted to clarify that. How we did this work, so the methodology, well, I will briefly explain it. We started with case studies. So these were actual plants that are in operation, and we needed to have some certain relationship with the owners or the operators in order to get important information about the design. So we defined some plant parameters that were or usually are requested at the simulation tools in order to build the model and simulate it. And then we did the simulation in different software. By we, I don't say this core team that I mentioned, but all the many participants that they have licenses of commercial software or even in-house software developed. So they said, okay, I want to simulate in my software and give me the plant parameters. They did that, and then they submitted to us all the results. We made a comparison of all the results, and on that point, we could identify some sources of difference. This was mainly collecting information, all these stages. We also did a lot of bilateral meetings with the analysts, so we could directly ask, why do you think we have this difference here? Is because you did an assumption, or is because the limitation of the software? So we collect a lot of qualitative information about the sources of difference for the energy yield within the different softwares. Then with all that information, we define some assumption scenarios. That being, we created in one tool a very detailed model, including everything that could be possible, and then we started relaxing some of the constraints. For example, trying to emulate what happened when you cannot model something because of software limitation. We did that for all the case studies that I will present next, in order to understand how the technology impacts on it, how the load and the integration scheme also affect it. And from that results, we obtain the overall results. So it's a guideline that I will also show you. So for the comparative study, we had 4 case studies. The first one is a flat plate collector plant, fixed, and it supplies heat to a copper mine in Chile. This is the picture. The second case, it's a flat plate collector, also solar field, but it has one axis tracking system to supply heat to a paper mill in France. And this already was, even it's a simple technology, it was not easy to model in all the available software because it's not common to have a non-concentrating solar thermal system with tracking system. So it was also interesting to do this. This is a Fresnel collector to supply direct steam to a process also. And again, a different technology with different temperatures, and also storing steam is a challenge by too many softwares. And the last one, it's a parabolic trough that supplies heat to a dairy factory located in Switzerland. So the table here shows the software or tools that we analyzed for each of the cases. Of course, the most more tools are better, but it was not always possible, mainly because of limitation of some of them. In addition, we had, for example, for Transys, which is a very you can make a very customized model. We had different results from depending on different analysts. So we also can kind of assess the impact of the human, and we wanted to avoid that in the later stage. So recently, the guideline, this is one of the tangible deliverables of the subtask. It's out, it's ready. So we have the draft version. In the next days should be the final one. It presents the methodology that we applied, the detail of the case studies, like all the parameters that I mentioned, and also the integration scheme, which is also interesting, and it's important to know the different on the technologies that are applied. We did the first assessment of the deviations that I just mentioned, and then we related them and tried to list the most common assumption and how they impact in the energy yield. We also present for all the case studies the different scenarios of this induced error assessment. I will show an example just after this slide, just to understand. And finally, some recommendations. These are just recommendations because it's not possible. So chip plants are very customized to the client, so it's not possible to have just very strict kind of articles. It's better to have just some recommendations, and there's no standard nowadays. So for the scenarios, we, for example, consider some parameters. We identify these from the exchange with the other analysts, and some of them are listed here, like time shifting, and this is very easy. For example, when the software is reading the meteorological file with a different time or a delay, a gap that can show some problems, and well, thermal capacitance, the pipes insulation if there is a test node, and the load. Also, that's important when you have ramps or if it's a flat load. We have just seen that the effect, for example, in the presentation of Felix. So we just consider some of these parameters, and we then perform the comparison using some statistic metrics, and we separated them between according to the time scale. So, for example, we use solar fraction for total of annual and monthly values, and also the energy delivered on daily scale. But we know that totalizing the energy also hide a lot of variation, so we consider also an hourly scale. And we employ dynamic time warping and residual values to analyze this. Of course, it's a lot of information to introduce it, but we could understand and identify some sources of uncertainty with the hourly values. The comparison methodology that we developed it for case study A, and it was a lot of effort to trying to understand and to decide which are the best statistic metrics to show this information. We obtained we wrote a paper that has open access. At the end is the link. And we also coded everything in Python to perform automatically all the comparison of the different results that the different analysts were sending to us. This is the example, for example, for case study A. It's a table. All the columns show the different parameters that for this case study we consider. So scenario 0 would be the reference. So these are the values considered, and the other scenarios are varying one parameter. For example, time shifting, these are the variation of this value, thermal capacitance, and so on. So these different scenarios show different results regarding the energy to load and the difference comparing with the reference. And for example, here these scenarios consider the thermal capacitance at the solar field. So there's the reference value, and then you can have like no thermal capacitance, or having 150% more, or even 300% more. And we can see in the overall results on annual values that the difference that you can have is about less than or about 3%. That in simulation is not that important for the overall results, of course, depending how detailed you want it, but it's not a huge mistake considering that you are having an error of 300% on thermal capacitance. But for example, if we consider the number of nodes of the thermal storage tank, if you have a stratified tank and you cannot consider all the number of nodes that you want, this could lead to a quite important error, for example, and that is just because it's a limitation of the software, or maybe because you could consider that it's not that important, but here the results show that it could be you should put more effort in that part. So this would create a guideline in what to put more effort and focus when you have, of course, limited time and limited software, or there are limitations of the software. And also they are separated by technologies on the four that we have studies in this case. Just to show you the hourly data, so we created some residual values plot, and here we can show, for example, these are the number of nodes of the thermal storage, and even for 10 nodes, you could see that the overall annual value is not that much, but you have underestimation and overestimation along the day. So the total value, of course, is not that much, but on hourly basis, it could be important. And if you have in a process where you are supplying this heat, that could also be a problem. So this analysis was also done for all the parameters that we observed, and it is also reported to understand or try to put more effort in those that you can see that impact the most. For example, here also the effectiveness of the heat exchanger. It could depend on the parameters and also the technology. An additional outcome of the work that we have done is to update a table. So this was one of the outcomes of task 49. We took this. It's a list of available software to simulate thermal systems, solar thermal systems. We updated it. Of course, the software have improved in these years, and also they have more capabilities, so we can see, for example, some of the features of the software. They are sorted, and as I said, they are not ranked, which is the best one, but you could see more or less if it could be feasible to model your system in some of this software. It has three. Well, this is the complete table. Of course, if you have any input, we are very open to get it, some feedback, and to add more software. If you have one software, also to include it in this list. Just the final remarks. So I just want to invite you to participate in the second stage of the task. So it's the next year. We will be working on monitoring the solar thermal system during the operation stage. Most of the work done was during the design stage. And for that, our next subtask meeting is this Friday, 2 p.m. Central European Time. If you're interested to participate, we just discuss. It's very, very friendly environment. Just send us an email and you can. We will include you in the meeting. All the information that we have shown, the outcomes are available or will be available at the Task 64 website. Here is the link of the open access paper that I just mentioned, which has all the methodology, and it's very academic, so that's why it's not. I don't have time to show it, but here's the link if you're interested. And we also have performed some presentations at the ICES conferences, Solar Congress, Eurosam, and also at the CS conference. I'm very open also to question, and I hope it has been interesting for you. And we have an interesting Q&A session. So thank you.
Yes, Alan, thank you very much. This was great, great insight into, a very difficult topic of simulating complex ship systems. I think important work that a task can do in a very good way, because you have these over institute network, so a lot can contribute. Hopefully somebody is very spontaneous and can take even part in your meeting on Friday. So we come to our third speaker for the day. He is Wolfgang Gruber-Kratzel, and he's research assistant and project manager at the Austrian Institute, INTEC, since 2013. His focus is on industrial systems, including energy and resource efficiency and innovative process and supply systems. He is also supervising projects focusing on industrial and municipal wastewater treatment plants. He is one of the initiators and long-term administrators of the ship-plant.info database, which is an online database which includes a large number of ship plants worldwide. And I think his topic of today will base on looking into this rich database. The title of his presentation is Ship Successful Plants Worldwide. Wolfgang, the floor is yours.
All right.
Yeah, perfect.
I hope you see my correct version of the screen.
Yes.
Perfect. All right. Then welcome to my presentation on ship successful plants worldwide as part of this academy. I'm glad I can also join my excellent speakers. It was very interesting also to listen again to Alan and Felix. I want to go not so much on the detail of single simulation or concept designs, but rather what has been successful so far. Starting at this graphic, the potential is huge for thermal demand in industries. I think many have seen this chart before. It's an excellent chart showing just how much potential is actually for solar heat in industrial processes. 1/3 of the total final energy consumption is for industry, and again 3/4 is for thermal, so for heat delivery. And then again, looking at the temperatures, again a high share is for temperature levels that are suitable in principle for solar heat. So I know some people that are joining know a bit more about solar thermal. Some maybe don't know that much, but yeah, of course we can think of a lot of barriers, a lot of problems, or a lot of challenges. But we wanted to focus also in this task on yeah, the success factors for SHIP. So I want to present today some of these success factors on existing SHIP plans, what we have learned from our SHIP database, as Babel has mentioned. And this is why I want to show you some data from these existing plans, some examples, and see what kind of success factors we can derive from them. So this is the link to our existing database. It's this the URL ship-plans.info. You can see a screenshot of the map worldwide. More than 400 plans have been documented so far. You can filter for countries, from operation time, industrial sector, unit operation. With this we mean different processes that are targeted. You can filter by collector area, by collector type. Also point of solar heat integration, which was an important work of the previous task on SHIP on task 49. You can see here an example of the different integration schemes on supply level or on process level. And last but not least, you can also filter by solar thermal engineering companies. So those companies that actually implement the successful implementations. This data from the SHIP database goes directly also in a publication that Babel has already mentioned at the very beginning. It's the Solar Heat Worldwide report, which is published also from our institute. Werner Weiss is the main author here, and I'm also contributing in terms of the SHIP data. So in March 2022, this was the last cutoff date, we have documented 394 plants worldwide. In the meantime, a lot have fortunately we could add to the database in the meantime. So we are already looking towards the next publication in 2023. So more than 1 million square meters of cross area have been documented there. Looking at this chart with different size categories, we see that only 3 plants are in this largest category with larger than 30,000 square meter of cross area. And many know maybe that the reason is that it's related to one plant that has 59% of installed power of all SHIP plants. This is the Glass Point system in Oman, which is very huge in comparison to everything else. So all the statistics are somehow a bit difficult to show, because like one plant of this 394 has 59% of an installed power. On the one hand, it dwarfs what has happened, what is happening at the other plants. It also shows the huge potential it can have if the right potential is if the right system is applied. But I also want to highlight that all the other plants, they are success stories, of course. And there's, as Felix has shown, I think that there are many plants with a lot of roof area available for solar thermal. But well, one success factor here, of course, was the turnkey solution. GlassPoint is delivering steam and not collectors, so it has not sold the collectors to the client, but rather it has sold the steam. Another, so this is like, I want to highlight as one success factor, this turnkey solution, selling heat, not collectors. We are doing a lot of work with industries, also not only about solar process heat, but also of heat recovery and these hybrid systems with heat pump solutions. And of course, for industries, long-term energy security has gotten increasingly important. So having a stable energy price is really a selling point, an increasingly important selling point for industrial clients. They are looking for safe energy supply. Another example is the Molterie in Issoudun in France, which has been implemented in 2021 by the collector manufacturer Savo Solar and the ESCO New Heat. They are selling, New Heat is selling the heat to Beaumont, which is the Molterie here. I'm very happy that this plant is realized. I was at this plant 4 years ago doing a feasibility study, and now it has been implemented. So it's also, I think, a great success that this was possible. Yeah, also one of the largest collector fields in Europe and worldwide for SHIP. So looking again at the perspective of the end users, they want to know if SHIP is a reliable solution, if it's a simple solution, and if they are the first one to implement, or if it has been done before. So all, we are R&D and suppliers in this research task, and we can say yes, SHIP is reliable. It's also simple, one can argue, but still it's a simple technology that can be implemented, and there are experts that know how to do it. And no, it's not the first time it is implemented, but it has been done before. Then the end user is looking at the financing. It's looking at the CAPEX and the OPEX costs. You can see that, SHIP is rather cost intensive upfront, so very high CAPEX cost, but low OPEX cost. So we try to avoid looking at payback time, but rather look at levelized cost of heat, because this shows more the true cost of solar heat in industrial process, especially if you can provide turnkey solution. Of course, especially for Europe, but also other regions, this has also changed dramatically, while gas price has, from looking at 2015 compared to now, 2022, the gas price has increased significantly, while SHIP has more or less stayed on a same level. So this is, I think, and we think, important selling point. On the one hand, secure energy supply, increasingly higher renewable shares, which is very important, and lower prices. What else can we derive from the SHIP database and the data from there? Again, a chart from the Solar Heat Worldwide from 2022, which bases on our SHIP database. We can see a high number of flat plate collectors. 174 have been implemented as flat plate collector, 59 as Bollock trough collector. I think this is also interesting, but also evacuated tube collectors and other collectors have been implemented through all collector types, in fact. What we have seen in this last year is more implementations on systems with higher temperature on collector temperatures. So Fresnel collectors, parabolic trough collectors, but also this example, vacuum flat plate collectors that can provide up to 180 degrees. We have seen multiple implementations there. There, the integration is simply easier. You can integrate on the supply line on the utility side of the industrial plant. You're talking with the facility managers and not so much with the production managers that are dealing with the product processes, really doing the product. So it's much easier to actually integrate a larger share of the heat. and cover a larger share of the heat demand, which also is also reflected in the economy of scale. So you can install large systems. Well, and future innovations, of course, is the hybridization with heat pumps and also seasonal storage with excess heat combinations. So excess heat, of course, is also a very important aspect. A lot of it is at low temperatures from cooling systems. So integrating this together with heat pumps and solar thermal can result in very high renewable shares. So this is then really the possibility of providing high renewable shares with cost-effective solutions that would be really interesting for the end users. Next, shipper sector, we can see that we have a high share in the food sector, 130 plants, and also the square meters is quite high. Again, mining is the most important one, because again, there is this one large plant included, and also the second largest plant, which Alan has also shown as a case study. This is the Chile copper mine, is the second largest plant with more than 30,000 square meters. So this is very dominant. But besides this, we can see that the food sector is also a very interesting industrial sector for solar heat in industrial processes. And we can see that some companies have really achieved a high number of implemented systems. So they have multiplied what they have done before. They have a high standardization in their workflow. And here I want to highlight the success story in Mexico with two, but also some more companies, but basically two companies that are having the highest market shares there, and they are in competition. They have reduced planning costs because of doing similar integration schemes. Again, when we look at the integration concepts, a lot of integration on supply level at low temperatures was possible, with lower solar shares, but still, and this is why also smaller systems, but still are high standardization, high multiplication. They have been in contact with a lot of industries, so they know how to promote the systems and how to play the selling points. So there's a high replicability in industries. So I think this is also important, that if we reach a tipping point for solar companies, that really accelerates their business model. If they can have increasing numbers of systems implemented, then it increases the chance of snowballing for larger market shares. I wanted to start with all these three success stories, just a few examples to highlight this. And now going to what we are doing in the task 64. We have seen subtask A with Felix and subtask C with Alan. We from AEE together with Fraunhofer ISE are leading the guideline to market. So we really want to make sure to promote SHIP also the right way, to promote it as a solution for the industry. This is the goal we have here. So the big picture is addressing the relevant aspects and barriers, and place SHIP as a core part of this hybrid industrial energy systems that has been presented before, being a platform for researchers, technology suppliers, project developers, and end users. So also today is a good chance to promote this again in the final year of the task. If you're interested in our activities, please also contact us, and we can collaborate here, which would be also very interesting for us in the final delivery, which we are doing, which is a position paper on SHIP. And I think the more voices we can include there, the better it is to speak for everybody. These three aspects I want to highlight: innovation, competitiveness, and financing options. this is also reflected by these 3 success factors I've mentioned. So innovation is still necessary. SHIP is a technology that can be implemented as is shown in the SHIP database. It is competitiveness is important. Yeah, and increasingly looking at financing options. So those were just a few examples. There are many more examples on our SHIP plants.info site, which is done by us. It's a plant-by-plant documentation, but I also want to highlight that there's also Solar Payback, which is done by Babel app, by Solrico. There's also, she's doing a yearly solar supplier survey. So there the suppliers are saying how many plants they have submitted. Also, some of those plants come with fact sheets and pictures. And we collaborate also between these 2 data sets on data acquisition and also cross-referencing. So for example, if you go to the Solar Payback side, if you look at the suppliers, you can select some of the solar suppliers. And for example, you can select a company. And if you click here on the link for references, it refers to our SHIP database, where we have then a plant-by-plant documentation of this solar supplier. So kind of cross-referencing of this information. Actually, we can cover currently 82% of the collector area that is mentioned by the solar suppliers. So there's a gap, but also we have rather larger systems here documented. And of course, yeah, some will always be missing. We rely here also on all of you in the audience. So if you know of any plans, then please contact me. This would be very helpful. We try to build up collaborations throughout the whole industry to make sure we can get all the data that is needed to for that purpose. Also, you can profit from this information. You can get to Solar Payback for pictures and fact sheets. So for basic information on suppliers, and you can also go to the SHIP database, where you can get a bit more detailed information on the actual location, also some pictures included, more information on the size of the systems, the storage system, the process integration type, lessons learned, and other information on the plants. A small teaser also from our side, we want to relaunch our SHIP database. Will be the same name, but we have implemented it many years ago. Now it has become the time to relaunch it a bit. It will have more features on filtering, a new map layout with plants location, automatic charts and data exports for other researchers to use this data for their market research or analysis. And like it is now, you can add and edit new plants. We are always looking at any addition, so and will then publish it, so to make sure that there are only plausible data published. And well, we will release this in 2023. It's currently in development. So with this, I want to end my presentation. If you are interested in any information on the SHIP database, I highly welcome you to contact me if you want to know more about it. And well, thank you for your attention, and looking forward to your questions.
Yeah, thank you, Wolfgang. Very nice to hear about all these success factors. We had at the beginning of your speech some questions on what is this success factors, define it, but I think you have done this very well in the sake of your presentation. So I think it was a bit provoking to talk about successful SHIP plants, but I think you mentioned some really nice case studies, and your database is for sure very important for the whole SHIP sector to develop. So I ask now all the 3 speakers to come up on the floor and get their cameras on again, because we have the Q&A now. Hello, Felix. Hello, Ellen. Yeah, we would like to start with Felix. I think there were some principal questions on your presentation, Felix. We had a participant wanting to know how you define these clusters. Can you say a word on these?
Yeah, of course I can. So yeah, we had this very big database of around 800 profiles that we got from utility providers. So that was the only option to get that many profiles on one step. And then we had the basic assumption based on previous work that there is a correlation between the daily heat demand and the ambient temperature. And because we had already this assumption or this this research question, if this is really the case, we did a cluster analysis based on a k-means algorithm in Python to and then this algorithm tried to define these clusters and defined that 4 clusters is a reasonable number to differentiate all these different heat demand behaviors. And then we did these regression functions for this. So that is the basic methodology. I think we could talk about much more technical details, but I think that would go a little bit too far. But okay. Therefore, I would to point out the paper that I also referenced in the slides. So I think everybody could follow the link to get more insights on that.
Okay, thank you. There's another question, Felix. How can you explain the non-heat dependence of some industries, for instance, food and beverage, on ambient temperature? Although, in brackets, heat pumps are probably used for thermal regulation.
Yeah, so basically what we had was the not really the heat demand, but the gas consumption of all these companies. And we assumed that that the first approximation is quite good to assume that all this gas is used for heat generation. So there might be some applications where it's also used really at that's really used in processes, but basically the majority will be used for heat production. And then if you have a look at the food and beverage industries, or especially in the beverage industry, the main heat demand is for water preheating or water heating. And here the ambient temperature does not play a role. So perhaps in winter it might be that the cold water temperature is 2 degrees colder than in summer, but more or less it's constant. And it's throughout the year, it's always that you have to heat up, I don't know, 10 cubic meters per day from 10 to 90 degrees Celsius or so, as an example. And other sectors, for example, the production of cars, here we do not really have industrial processes as we have them in mind. There might be a bath heating, so there it's more or less constant throughout the year, or there might be some drying processes, but the space heating demand or the heat demand due to big ventilation systems is really dominating, and that's really the difference. Do we have a process where we just heat up something, then there's no correlation to the ambient temperature. But if we really have anything to do with the boundary conditions, that we have to heat up the cold air outside, or that we just have to heat up the production halls, then we see this seasonal behavior.
Okay. A third question concerns your chart where you showed the levelized cost of heat when looking into a heat pump capacity factor with, like solar thermal, and you made it optimized at 0.6, but the person asking here, the chart showed that LCOH were lowest when the heat pump category capacity factor was 0. Does this mean it was better to have just solar and no heat pump? You remember that?
Yeah, so the economic evaluation of heat pump is always depending on the relation of the gas price and the electricity price. And we did also here some work within that paper, and basically it was we used some mean values before the crisis, and there it was not yet feasible to use heat pumps compared to gas boilers, and that's why this is a result. But we were not really interested in the absolute values, but more in the tendency, what is happening if we increase or decrease the heat pump, and what is the behavior. And what we could show that by increasing the heat pump size, the levelized costs are partly increasing, but they are not doubling or even more. But the effect is that by increasing the heat pump ratio, we could cover much more heat with low emissions. And so that's basically what we target at. And in future, or now we see what can happen with the energy prices in very short time, and now the economic evaluation will be completely different. So it was more about the sensitivity than about the absolute values.
Okay, I got it. Alan, we have some challenging questions for you here. The first one says, in your experience, which of the softwares analyzed in your research paper provides the best compromise between flexibility and accuracy in the analysis of solar thermal systems integrated into industrial processes?
Yeah, it's a challenging question.
Yes.
Well, first of all, as I said, we're not into ranking these softwares, but also I think it's not possible from our results to compare them directly, because it could depend a lot on the technology you're using, what is on the load side. So do you need water, or do you need a special oil, or even steam? So I think there's no one answer. And I'm not a selling person, so I'm not trying to sell my software. But I think it first would depend. You need to see which is the solution, the plant type you want to model, and then filter which softwares are capable to do so. For example, for concentrating system, I know, and we have talked with a lot of developers that couldn't find couldn't find a software that fit in their requirements, so they developed their own software. Some of them with in-house software, and some of them perform better than some commercial software. But of course, that are very customized software, and maybe if you use that same model in a different type of collectors, won't be better. So I think that in terms of flexibility, of course, commercial software could be the better, because they are developed to provide different solutions. But yeah, I think it's not possible from the information that we gather to just
say this is the one. Okay. Another challenging one. You mentioned that the TRINSYS results depended heavily on who was running the simulation. Can you discuss briefly your preference for simple versus detailed modeling for these systems?
So, well, in TRINSYS, you can use different libraries with the components. So it's a component-based software. It doesn't have preset models like other software like Polysan or SAM even. So it depends on the model that you're doing, and you have different options to solve one same problem. To I don't know, if you want to model pumps, you can use different type of pumps or different type of controllers. So you can use it, you can do it, or the model, you can create it very simple or more detailed. What I was saying, using the different analysts and different libraries, is that we try to identify where are the problem or the differences coming from mainly, but not stating that one is the best than the other, and that is what we want to do in the second stage. So trying to, during the monitoring, to have real or actual data to compare how it's performing the simulation that we're doing, because on a design stage, you just propose a solution, and then on the operation you could see how it works, maybe on the overall values, like the annual value or the monthly value, the energy fits, but when you see on the detail, if it's working as same as you model it and the simulation results show, maybe it's not the same. So just to answer, the transits, we use, I think in the 4 case studies, about 8 different models on transits from different people, and also using different types. Some of them also self-developed because they were not available in the commercial libraries.
Okay, interesting. Wolfgang, how about the SHIP, your SHIP database? Does it say anything about the share of different collector types, like flat plate versus vacuum tubes and concentrating ones among your registered projects?
Yes,
and can the filtering be done, was the second question on that.
Yeah. So the first part, yes, you can filter by just showing the flat plate collectors and just showing evacuated tube collectors, Fresnel, parabolic collectors, and air collectors. And then other collectors where we have some dish systems, for example, from China, India especially, and yeah, different areas. So I've shown you the chart also in the slides. For example, for the Solar Heat Worldwide report, what you currently are not getting is like this chart automatically by filtering. You just get like the adapted list with only flat plate collectors, for example. Yeah. So we try to work now in the relaunch that these automatic charts are also adapted when filtered for countries or collector types, process integrations, and so on. So I will take this as a confirmation that this is a good way to go forward.
It's an important
this
feature,
could be helpful.
exactly.
Yeah.
So how about unclazed collectors? We have a participant saying that this might reach the lowest cost on, like preheating, so more only groundwater.
Yeah, unclazed collectors is very limited for SHIP due to the low temperatures. So I mean PVT is on the rise, is not it's also with low temperatures, but not so much for SHIP implementations. At least I don't see that now in our SHIP database.
It's not that represented yet. How about costs? We were asked here for technical cost assessments. Is this possible with your database?
Felix is smiling, so he wants to answer maybe.
You did the last cost.
It's your question.
Yes. Okay, grab it.
No, we do collect economic data from these implementations, and we try to analyze it. We also break it down to the solar collector field, the process integration, the storage, and other components. But it's a very wide spread of costs, also specific costs per square meter. So it's not easy to derive statistic representative data. However, it's still interesting to see at local solutions. Again, I want to highlight Mexico, that we also ask for subsidies. So a lot of implementations in Mexico is done without subsidies. So I think also it's interesting to look at the data at the SHIP database, maybe not for statistical purpose, but statistical purpose is not the only purpose for the SHIP database. It's also showing, those are implementations. They are successful. They have been done in certain region, in certain industrial sectors. Have a look at them, and maybe you can derive some information out of it. Yeah, but statistically correct, like correlation of sizes and so on, it's not so clear, but still information available, I would say.
Okay. Felix, you want to add on this?
So no, I was just laughing because cost is always what's interesting for everybody, and especially in these times, I think it's really difficult to make analysis based on historical data, because everything is changing that rapidly. So that was basically just the reason why I was laughing.
Yeah.
Okay.
But we know it's important, of course, and we try to improve there on this regard. Yeah.
Okay. Felix, a general question for you. Which are the principal obstacles in the formulation of clear design strategies towards the feasible integration of solar heating technologies and heat pumps in industrial processes?
Yes, I think one basic problem is really the very big variability in industrial applications. So we talk about different sizes. So from, I don't know, 1 gigawatt hour per year to 10, 50, 100 gigawatt hours. So it's always, that is a very big parameter in the scaling. Then the boundary conditions are always very different. So we made now the steps from having no real idea of industrial load profiles to at least give some very first hint how to start with that. Then it is a question: do we have excess heat potential, and how is the relation of the excess heat potential to the overall heat demand? Do we see a seasonality there? What is the temperature of this excess heat, and what is the temperature that we need to reach? So these are all very important parameters which always influence the overall system design. And then, yeah, one problem is really how to decide. So we can always define a kind of optimized system, but the question is always, what is your target function? So if you just want to reduce CO2 emissions, then the costs are going up and up, and then you always have the problem what we see right now. So if we would have optimized that 1 year ago, the result would be completely different today if you would have optimized with the target function focusing on economics. So it's that's why the spectrum is really huge, and then it depends what is your target function, and that is as it is not very easy to generalize all these parameters for all solutions. We always have these tools are trying to do that, but we are not yet at the point that we can really say just give the input into that tool, and then here is your however optimized system. So that's really a problem.
Alan, did you challenge your simulation tools with this question of giving you access to hybrid solutions or good results for hybrid solutions?
Sorry, I'm muted. I was muted.
Yes.
We haven't done that during the task, but we have discussed that, and it's also interesting. I personally have done it, and I think it's a challenge for all the commercial tools that are available. Usually they don't have integration, or if they have, it's just at the end. So it's like they simulate both systems, and then at the end they adapt the energy supplied, but not a clear integration, how we would think about it. But yeah, so far it's not in the scope of the subtask, and we haven't done it yet. But we have discussed with Felix, also Jose Miguel Cardemil, that it could be interesting.
A good option
to
look at. Okay. Felix, you are asked, are available speed heat pumps included in your conclusion on slide 8? Or if not, would they change conclusion? I'm not sure what slide 8 was, but you might know.
Yeah, slide 8 was about the levelized cost of heat, but about what kind of heat pump speed?
Speed heat pumps. Oh no, available. No, variable speed. Oh, sorry. Variable speed heat pumps. So that means modulating speed pumps. Sorry,
Yeah,
I was reading
so
this out wrong.
they are included. So we did the assumption. I think it was down to 50% of the net capacity that the heat pumps are able to modulate. But yeah, so they are included.
Okay. Wolfgang, a general question again regarding electrification of the ship sector. Do you, or well, of the industrial sector, have you thought about this potential in terms of which share might be electric and which share might be done by renewable heat in the future?
We are looking at this currently on a national basis. So actually, yes, we have some ideas regarding this. It's called Transform Industry. So it's really about decarbonizing the industry of Austria. In this case, also looking at European level, and of course, electrification is a big topic there. But I think what is kind of not forgotten, but that it's getting also very expensive, right? If everything is electrified and not the most efficient way. Also, heat pumps need heat sources, and also they are limited. So solar thermal can play simply a role in that case in the integration scheme Felix has shown, where really solar thermal is the energy provider in this regard for the heat pump as a heat source. So I really think that ship can play here an important role as the more cost-effective solution here. Yeah. Full stop. Yeah.
Okay, that's a good final message, actually.
Yeah, because I think, of course, electrification is a trend, and hydrogen and so on. But we see now with industries that are really serious with their decarbonization strategies, that they are not comparing the cost for ship with natural gas, but rather with hydrogen already. You know.
Mm-hmm.
And they are really serious about this. It's now a trending topic, and they are seeing, okay, ship can do the same, very much more cheaper. It is more expensive maybe than natural gas, but it's cheaper than other decarbonizing strategies.
Yeah, good. Yeah, we are in the big circus of from green hydrogen to waste heat to electrification in the industrial sector, but I think all is necessary. This was a very interesting Q&A. Thank you very much to all our speakers. I hand over to Arabella, and I wish you all a nice rest of the day.
Yes, thank you very much, Babel, and thank you very much to all of our speakers and of course the audience. Thank you for this very good Q&A. I want to close with a few final remarks. We always get loads of questions. Yes, the webinar is being recorded. Yes, you will get the recording, and yes, you will also get the presentations. So no need to worry about any. And I think Wolfgang, Felix, and Alan, they all said that they are happy to hear from you and happy for any other questions. So those will be made available soon, both on the IESES homepage as well as on the IEA SHC homepage. Please give us a few days for that. We have to edit the recording, and then it's all going to be there for you. And then finally, we are almost at the end of 2022, and we want to announce one last final webinar for this year. You know, IESES does webinars every month, and we have the IEA SHC for some of the months. And in December, we will actually have the partnering team, that's the IEA PVPS, and they are task 16. And the topic of the webinar is going to be all sky imagers benchmarking. So the webinar is going to be on December 15th. You can see the link to register on the slide. Just go to the IESES homepage, and we will also send out an email invitation to you. Yes, and with that, thank you very much for joining us. If you want to share any feedback, please go ahead. You can reach us at public.relations@ieses.org. And of course, we are on all the social medias. And yeah, a big thank you again to our speakers, and talk to you soon. Bye, everybody.
Bye-bye.
Thank you.
Thank you. Have a good day.